Okay, thank you so much. Good morning, everyone. Duan and I will be chairing this session, this first session in the morning, and which has very interesting presentations. And I will give the microphone to my colleague, and he will make the introduction. Thank you. Good morning.
Okay, good morning. Welcome to session 3. So we had myself, actually, I really enjoyed yesterday. It was wonderful. I learned a lot from the overview talk by Matt Anderson, and also session 1, wonderful talks, the global perspective, and the afternoon session, the socio-economic impact. So today, the session 3, the theme is the confronting impact of climate change and human activities on data. So we have 3 speakers. So the first speaker is Dr. Fuquiang Tian from Tsinghua University. He is going to talk about impact of water resources development on hydrological regimes of Mekong River. So Dr. Tian, you already have his information. You know, he's a professor in Tsinghua University and also the vice president of International Association of Hydrologic Science. So welcome. So the podium is yours. Okay.
Good morning, everyone. Thank you, Chair, Dr. Duan, and thank you again, Professor Sarush, for Chair organizing everything and sharing again. So today I will talk about some recent research on impact of water resources, development, and climate change on hydrological regimes of Mekong River. So before I go into details, I would first like to cite the statement given by Ostrom, Elena. She said, building knowledge and trust is essential for solving the collective action problems. I like this sentence very much. For me, I understand the transboundary water management is collective action problems. So we need trust for collaboration, of course. So to build the trust, I think the knowledge building knowledge is also a very important basis. So following this notion, the Mekong River Commission and the Lancang Mekong Cooperation Mechanism, they launched a joint study 4 years ago. So the topic is the similar title with my presentation. The climate change, human activity, its impact on hydrological regimes and the adaptation measures. So we have. I'm very happy to be invited to lead this joint study from the perspective of the university. It's a more neutral position. So we have finished the phase number 1. You can see the technical report, and now we are finalizing the report for phase number 2. So most of my presentation results are coming from joint study. Yeah. So a little bit overview again on the Mekong River. So actually, the upstream of Mekong River is called Lancang in Chinese, Lancang Mekong River. So this is why we have the Lancang Mekong Cooperation Mechanism covering the whole basin. So this river is very long, over 4,000 kilometers, draining an area of over 800,000 square kilometers. So it supports 70 million people and directly, and many more indirectly. So we all know it's tropical monsoon climate, cover most of the basin area. And we have the flood pause every year, the high flow in the rainy season, low flow in the dry season. So this flood pulse also very prominent in the Tonle Sap Lake. The lake is a connection between the tributary and the mainstream. It regulates the reservoir, the sediment, and very important for the fishery in Cambodia. It provides 70% protein, animal protein for the Cambodia person. So the Mekong Delta, it's a low relief, tidal influenced plain, it's very flat. It's the food basket, of course. So the delta stability, it depends on discharge, sediment, bordage from the upstream, also the coastal forcing from the sea. So we have experienced quite a lot of water resource development in the past decades. One of the most important activity is irrigation. So as you can see from the very right map, the green dot, it's existing irrigation project, and the red dot is a planned irrigation project. We can see agriculture is very important, and irrigation also important because we have the monsoon season, dry and wet. So this data from MRC data set, and we can also see the significant land use change during the last a couple of decades. So different part of the basin, they have different trend. From the upstream, the Lancang part, the land use remain dominated by forest and grassland. It's going downstream, more land converted to the cropland. So we can see from Paxi to Sangchun, this part, 5% of the basin converted to the cropland. So another important human activity is the dam. So you can see also from the right figure, we have many dams commissioned and prepared, planned. So we from the development of storage, the reservoir storage, we can pick up 2010 as a division. Before that, no major mainstream dams. After that, we have developed a couple of major dams along the mainstream, mainly located in Lancang, in China's part. So, but I also want to remind you, before 2010, the tributary dam, the storage capacity is also reached 24.5 billion cubic meters, the tributary dam. So some of them are for irrigation and some of them for a hydropower plant. So after 2000, the mainstream dam, the storage capacity reaches 45, and we have another 30, almost 30 billion cubic meters on the tributary. So similarly, roughly, the tributary storage is roughly equal to the mainstream storage. So we also experienced the significant climate variation during the last 45 years. So the precipitation in dry season, wet season, both decreased. The recent 20 years, the 15 years compared to the previous 20 years. So drying up, this is a general trend during the past decades. So precipitation declining, and of course we have experienced more drought. The frequency and the severity both increase. Also, we show the spatial uneven trend. So more severe drought will happen in the middle part, and sorry, you kind of see my laser point. So the lower, middle and the lower part. So it turned more drought. So I think we are all carrying this scientific question. So how these water resource development and climate change impact the hydrological regime, and what are the implications for the sustainability. So I will show you the result for the stream flow, the sediment, also the salinity in the delta area. So I conduct this study by using data and the modeling. So we collect a lot of data from China part and the Mekong part. We developed the hydrological model and also the hydrodynamic model for the floodplain, including the Tonle Sap Lake and the delta area. So the depth 3D flow model would utilize for this purpose. We also included the coastal dynamics, incorporate 40,000 kilometers of canals and distributaries in the deltas. So a lot of data incorporated into the model. So this is give you some ideas of the accuracy of the model. There's a hydrological model. You can see the merit, the evaluation index is high, up to 0.9, and the depth 3D model captures the water level dynamics very, very well. And for the reverse flow between the lake and the mainstream, the onset of the reverse flow, I mean the timing, so we can capture the timing, the error, absolute error is 1 to 3 days. So yeah, this is the rating curve for the sediment. So I don't want to talk too much technical details. So I'll give you a general picture of the runoff generation across the basin. So this table shows you the axle is not axles, but yes, you can see it's about 10 hydrological stations, and the Y is the same. And this table shows you the contribution ratio of the major tributaries on different hydrological stations. So this figure shows you more clearly. So the Lantang Mekong, the Lantang part contribute 62.2% at Changsan Station, and contribute 92% to Sangting Station. It's I think it's inlet above the inlet of the delta area. About 10% water come from the Lantang part, and similar tributaries with I mean the similar contribution tributaries, including the Sengkong, Sempok, and other Nangang. These major tributaries contribute equally to the basin. So during the past 2 decades, because of dam operation, we can see the obvious shift of flow seasonality. This is the red figure shows you the monthly curve stream flow. We can clearly see the flat hydrographs means flat season flow cut off, and the dry season flow increase significantly. This is the result of the reservoir operation. But this shift, seasonality shift, attenuate when going to the downstream. You can see the result also. So this change not only caused by the dam, it's also caused by the climate change. The previous slides showed you the observed hydrographs, and we attribute the the reasons to climate change, human activities, mainly the dam. So you can see the dry season, the climate, human, above Jinhong station, the human, the dam operation increased the dry season, but the climate decreased that. In second part, from NK to NP, this sub-region, human decrease and climate increase a lot. So it shows the spatial variability of the contribution factors, similar for the wet season. And the similar seasonal shift also happened to the minimum flow and the maximum flow. So it means the high flow, the flood, the peak flow is cut down, and the minimum flow, environmental flow was increased significantly. So for the very important phenomenon, the reverse flow happened during the flood season. The water flow from the mainstream back to the Tonle Sap Lake. This is the reverse flow. So reverse flow is important for the ecological system and the fishery. So during the past 2 decades, from 2000 and to 2020, 10 years, we compare that. We can see the reverse flow, the duration shrink very substantially. The green bar, the green stick shows the past decades, and the blue, more blue, shows the 2000 to 2009. Yeah, it clears a shrink of the lake and the decrease of the reverse flow duration. Also, the accumulated flow, the water volume associated with the reverse flow. So which factor contributed to this change, the decreasing of the reverse flow? So how about the future trend? So I think we consider at least the 3 factors. One is the climate change. The second is the dam operation. The third is the sand mining in this area. So the left-right figure shows the elevation change of the riverbed. The red color, the dark color means the elevation change 10 to 20 meters. So this is this location is a confluence part of the river, the Tonle Sap Lake and the mainstream. So you can see the 10 to 20 meters lowering of the riverbed. So it impacts the reverse flow significantly. So we quantify the 3 factors using the model, do the scenario analysis. I don't know if you can see the red numbers at the lower left. The B is the baseline, the historical period. The reverse flow duration was 130 days. And C is the climate change. When we incorporate the climate change in the model for the 2015 to 2035, the duration was reduced by a couple of days, only 4 days, 126. When we consider dam, C and D, climate change and dam, the duration reduced further to 118 days. So I think it reduced, but moderately, mildly. And when we consider sand mining, the duration further decreased to 100 days. So it means 30 days reduction. And when we look into the future, 2035 to 2056, our simulation shows almost stopped in 2045. So 20 years later. So if we don't take measures, the reverse flow will stop in 20 years, so likely, okay? So this is reverse flow and sediment load. This figure shows the suspended sediment load, SSD, for the Crisis Station and Choi Chong Wash Station. The location you can see there. We can see before 2010, the average load was almost about 90 million tons per year. And after that, the past 10 years, it's become 65, roughly, like that million tons per year. It's reduced. Again, it's caused by many things together. The dam is one major player for this. This is the sediment from the lake. So it shows a strong variation. The message here is the sediment from the lake contributing to the delta is a very minor part. I mean, in total amount of sediment, about no more than 1/30. Yeah. So a little bit about salinity intrusion, and Stephen will talk more about that. So we simulate the salinity line. The line means you can see for different years to 1985, 2022, climate change in dams and all things together: sea level rise, land subsidence, riverbed lowering. So we simulate that line. The line means 4 milligram per liter. The water salinity level. So you can see clearly the land water shift of the intrusion line, the black line and the blue line, the distance is about 50 kilometers. So yeah, so and because we simulate in different scenarios, so you can see also the sea level rise, land subsidence, and the riverbed lowering contribute a lot to the seawater intrusion. So my summary, in my opinion, so the delta are cumulative effect of basin-wide change. So it's the receiving point of everything. So the delta sustainability depends on the whole basin's sustainability. And we should coordinate from the basin scale strategy to local actions. So the basin scale strategy includes the transboundary water cooperation, strategical dam planning, irrigation development. Also the local action, we divided the whole basin into several parts. So different parts, they should focus more on the specific actions, especially the sand mining in A10 area. So this number from some report, the delta sand mining is about greater than 60 million tons per year, and the confluence area is about 50 million tons per year. So the basin-wide strategy and the local action are both important. Okay, I think I can stop here. These are the papers I cited. Yes.
Right. Okay.
Thank you.
Okay, thank you very much. So yeah, we are like yesterday. We are maybe.